Welcome back to Project Pulse. At this point, we are done building the core financial model. In the following lessons, we will focus on running the different scenarios required by the case study and interpreting the results from an investor and lender perspective. For this section, we will work with a final end file model, which you can download at the beginning of this chapter. This final file includes two additional sheets, a dashboard output sheet displayed here and a scenarios output sheet. The core model logic is identical to what we built together step by step in the previous lessons. Nothing fundamental changes. The model is simply extended with structured outputs to analyze scenarios efficiently. If you're interested in learning how to build a dashboard like this entirely from scratch, our Advanced Renewable Energy Financial Modeling course walks through a full dashboard build in detail. And if you're new to this Deal Lab series, I recommend starting with part 1, where you can download the model start file for free and build the model alongside me. Link is in the video description below. And before we implement the final cases into the model, let's briefly revisit the executive summary of our case study. We have already completed the full model build. From here on, our task is to run scenarios across the 3 monetization pillars and assess how equity returns, coverage ratios, and risk profiles change. In this lesson, we will start with monetization pillar 1, contracted capacity revenue. Specifically, we will focus on the first 4 cases in the model, all within the full tolling structure. The 4 cases are first our debt base case, also referred to as the debt sizing case, our equity base case, which in our case is identical to the debt base case. Then we will have a debt sensitivity, which will be an interest rate shock where we uplift SOFR by 500 bips. And finally, we'll also have an equity sensitivity where we assume an additional 0.5% degradation per annum for our batteries. Now let's move back to our model end file and start implementing these 4 scenarios. And before we get going, I want you to understand the end goal, which is that by the end of this lesson, I want us to have the first 4 scenarios displayed here in the scenario output sheet. And right now we're in case 1, which is our full tolling case from a debt sizing perspective. And what we can do here in this sheet is run all cases up to a certain input amount. So I can just type in case 1 here, run all. And this essentially just copy and paste the hard codes in that specific case here in the output sheet. And by the end of all of these lessons, we will have 21 different cases as outputs so that decision makers can clearly see what kind of case we're looking at, full toll case, which perspective it is. In this case, it's a debt base case or debt sizing case. And then we have all key assumptions regarding the BESS. So we have a 200 megawatt BESS with a 2-hour duration, translating into 400 megawatt hours AC. And at the beginning of life, we have 530 megawatt hours on a DC basis installed. We will have outputs regarding the capital structure, return metrics, IRR, NPV, cash on cash, and payback, which we modeled in the previous lesson. Then key lender metrics are CFETs, term loan, DSCR, LLCR, and finally we will also see our revenue structure. So our capacity tolling agreement, resource adequacy, auxiliary services contract, merchant arbitrage, merchant auxiliary services, and our revenue put option. And finally, from a valuation standpoint or a sponsor standpoint, we also have enterprise value multiples. So this output sheet here will be super handy to compare all the different cases once we have implemented them all. And the following lessons will help you to understand how to actually use and utilize the model in practice. And this is the reason why here in case 2, our equity base case is identical to case 1. So what I want you to understand here is that if we switch over to case 2, we will essentially have all the same inputs. Scroll down. You will see that there is no additional input for our case 2, which means the inputs from case 1 are always picked up by default. So if there's no input for case 2, the case 1 inputs are picked up. And that is due to a if is blank offset function that we have implemented for our live case in column H. So column H is ultimately flowing into our operations sheet that we built together. And that is really important to understand for all our following cases. So if we, for instance, look at a resource adequacy plus arbitrage case, then for our augmentation, we will have to have a different input for each single case. Because if we were to say select case 6, and then delete our input for row 232, you will notice that it picks up the input for case 1 instead. So it's really important to understand that the case 1 inputs will always be the default inputs if the cell is left blank or empty in a specific case. Now let's switch back to case 2. And for case 2, all of our inputs should be identical to case 1. So if we hit the master macro, we get an equity IRR of 13.81%. Let's flip over to case 1, hit the master macro, and we get again an equity IRR of 13.81%, which indicates that both cases are the same. When I flip over, we get a check, which stems from our DSR LC copy and paste macro. So if you just flip over here, you will notice that there's a tiny bit of a difference because we don't round this delta here. So I assume this number is extremely small. And that is indeed the case. So we could even say that we round this number to say 2 digits. Or let's actually do 1. So that we don't get a check every time that there's a slight difference for our LC copy paste macro. Now let's move back. And what I really want to emphasize here is the difference in the debt sizing approach in these two cases. So there will be one major difference between a debt-based case and an equity-based case. So if we have a debt-based case, which is our debt sizing case, we in general always want our debt sizing in row 254 to be turned on, which, if you might recall, will lead to a debt sizing in our operations sheet. And for our equity-based case, we want to ensure that the debt profile is based on our debt sizing case and is frozen in that specific structure. So if that is off, let's trace dependence. We will see that in our debt sizing section here, where we copy and paste the scheduled principal repayments, this section will be turned off. And here down in row 564, our applied principal repayment will be based on our hard-coded lines that we get from our inputs time dependent sheet. And these hard codes, if we look them up in our inputs time dependent sheet, come from our debt principal schedule, which are basically just a bunch of hard codes for this specific section. And now there are two ways of best implementing these. The first way is that we simply pick up the hard codes from this row and paste them into the next row as hard codes, Alt-H VSV, because our case 1 is our debt sizing case. Or alternatively, what you can do is you can turn on the debt sizing in case 2. We can delete all of these debt schedules for now. Let's delete all of them, because in the following lessons we want to manually implement them for each single scenario that we will have. And then once the debt sizing is turned on, we can hit our master macro, move back to the inputs time dependent sheet, and you will notice that the hard-coded line has been pasted in this specific scenario. So let's do that one more time. Let's delete all of these inputs here. So right now you can see that case 2 doesn't have a hard-coded line pasted here. We can actually execute the macro in this sheet as well. So hit the macro, and you can see that now the hard-coded line shows up. And now that we have our hard-coded profile, we want to make sure that before we run our sensitivity, we will have to switch our debt sizing case back to off. Because what happens is that if we now were to implement a sensitivity, then the debt sizing would occur based on that sensitivity. So since our equity base case is identical to our debt base case, we can simply turn this off for now. Turn it off, which means we're done with our case 2. And now if we switch over to case 3, we don't yet have a hard-coded debt profile for case 3 yet. And I don't want to just simply pick up the hard codes from case 1. I want to demonstrate how you can do it through the inputs time independent sheet. So here we can turn our debt sizing on for case 3. Let's turn that on. And we get a warning here. The warning is turned on in case we are in a case different from our debt base case, so either equity base case, debt sensitivity, or equity sensitivity. So if this here is not a debt base case, so not a debt sizing case, but we select that our debt sizing case is turned on, we get a warning because we want to make sure that we are not accidentally sizing on a sensitivity. So what we'll do here is delete the sensitivity input for now, which means we don't get a warning anymore. And now we again get our equity IRR from case 1. So there's no further input except this one sensitivity that we had in row 298. Then we can go to our inputs time dependent sheet, execute our master macro, which results in the same depth profile that we got from case 1. So you can see these profiles are all identical. And these are the profiles that the financing agreement will ultimately reflect, because the financing repayment structure will be based on case 1. And now we want to understand, what if we freeze that debt, turn our debt sizing off, and then things go really wrong, and our SOFR forward curve, which was predicted to be around 3 to 4% over the next 20 years. What happens if we uplift this by 500 bips? So for that sensitivity, we will go into our inputs time independent sheet in our sensitivity section, and then we will add a 5% uplift. So this 5% uplift will then feed into our inputs time dependent sheet. You will see that our applied forward curve is now lifted up by 5%, which will ultimately in our debt section result in higher interest rate expenses, including our sensitivity. So you will see that our SPV now pays 50 million more in interest. And in our dashboard sheet, you will notice how our DSCR profile has changed significantly or worsened significantly. And in our cash flow waterfall, you will notice how our interest expense went up quite a bit. And to just demonstrate that one more time, we can flip back to case 1, which is our debt sizing case. And case 3 is after our SOFR sensitivity has been applied. So thankfully for this sensitivity, we do have a hedging ratio of 75%. So if we were to turn the hedging ratio down to 0%, you would notice that then the SPV would be really in trouble, because now we would pay 100% floating rate, which would uplift our total interest expense much more than if we have a hedging ratio of 75%. Because a hedging ratio of 75% means that for 75% of the loan exposure, our swap rate is actually applicable, and our fixed swap rate is 4%. And that demonstrates why most banks always require a minimum hedging of around 75%, that in case SOFR or your forward curve unexpectedly is uplifted by a significant amount, the SPV would still be able to repay debt without yet triggering any events of default. Great, let's flip over to our scenarios sheet. And what you will notice is every time we select a case, say case 3, let's delete all of these hard codes here. You will see these are all hard codes. And once we delete all these hard codes and we execute our master macro anywhere on our sheet, we copy and paste the current case that is selected. So here you can already see the different outputs, which come in quite handy. So what's interesting is that not only our DSCR worsens, but also our equity outputs obviously would worsen if interest rates would increase. Our levered equity IRR would go down from 13.8% to 11.5%. Our payback period would actually increase from 9 years to 12 years. And our cash on cash multiple and NPV would also worsen significantly. Great, now let's move on to our last scenario, which is case 4. So let's move on to case 4. And here we do have a degradation sensitivity already implemented in row 301. So let's practice again how we can get our hard-coded schedule. So we will delete the sensitivity for now, so that we ultimately can replicate our debt sizing case. We will turn our debt sizing on, execute our master macro, which ensures that we now have our scheduled principal repayments in our inputs time dependent sheet, right here in case 4. All of these line items are identical. Let's move back to our inputs time independent sheet. Then let's say if you ever forget to turn this back off for whatever reason. Now, if you were to implement a degradation sensitivity of 0.5% per annum, as our case study indicates, you would get a warning right here indicating that you should double check whether you're still in a debt sizing case. Turn it off before you hit the master macro, because the updated schedule and the inputs time dependent sheet would only be updated if you hit the master macro. But if the debt sizing case in our inputs time independent sheet is turned off, then we wouldn't hard code a new line item in inputs time dependent, but refer to the previous hard coded line. So now we can go back to the scenarios sheet, where, by the way, the output is now still based on our debt sizing case, because the last time we executed the macro was when we have not yet implemented our accelerated degradation. So make sure that once you actually run a sensitivity, that you also hit the master macro once, so that these hard codes here get updated as well. Now let's actually see what our accelerated degradation does. So we can remove these arrows, scroll down to our sensitivity, and let's see where this is flowing. This feeds into our inputs time dependent sheet. And you will see that we have an accelerated degradation multiplier integrated right here. And this accelerated degradation multiplier essentially feeds into our applied degradation, including sensitivities, down in row 41. So here we will take our actual applied live case in row 32, multiply this with our accelerated multiplier to get to 89.2%, and that then ultimately feeds into our operations sheet. In our energy section, and ultimately reduces our DC energy that we have available at the end of each period at an accelerated speed which in return should cause more augmentations. And now here something really interesting happens. So if we switch back to case 1, you will see this is our base case, assuming the normal degradation we would expect for a full tolling case. And now case 4 assumes that we have an accelerated degradation. An accelerated degradation means that we should probably have to augment one more time because our battery will not be able to sustain the minimum nameplate energy capacity at the point of interconnection as long as it would in the base case. So we would expect effective duration to decrease at an accelerated speed. Then our major maintenance reserve account would probably have to be built up earlier. And we'll probably also need 2 different build-up periods because we will have 2 different augmentations. And that's exactly what's happening. You can see that our effective duration is now decreasing at a much more accelerated rate. We now need 2 augmentations. And now look what happens to our debt section. So since we have not accounted for the additional major maintenance reserve account build-up in our initial debt sizing, but instead we expected the build-up to occur somewhere around here, our DSCR is really decreasing quite a lot in years 2033 to 2035, because in those years, we would now need to already start saving up for our augmentation event, while in the years where we originally intended to save up for the augmentation itself, we wouldn't need any of this additional cash anymore, which would lead the DSCRs to accelerate quite significantly, which kind of just showcases how careful lenders need to be when it comes to augmentations of batteries. That's why often lenders insist that the major maintenance reserve account should rather be built up earlier than later and not last minute before the augmentation event actually has to occur, because you can always let that cash sit in the major maintenance reserve account for an additional couple or 3 years. But if you don't have the cash available earlier than you would expect it, then you might really run into deep trouble and potentially not be able to make debt service for that save-up period. You can also see that right in that period, from 2033 to 2035, we are in lockup. So we would still have more than 100% of our debt service, between 106 and 107%. So technically, we could distribute a dividend to the equity investor, but you can see that our cash-on-cash yield in these years is at 0%, and that should also be reflected in our financial statements, where we should build up some cash in those years. So not only do we build up cash for our restricted cash account, our major maintenance reserve account, but we also build up cash in our regular cash account because we are in lockup caused by a minimum DSCR below our lockup DSCR. Great, now let's move back to the scenarios sheet, and I just want you to see one more thing. If we delete all of these hard codes right here and say that we now want to run all cases up to case 4, which we implemented right now, we could simply hit run all, because right now we have successfully implemented our debt schedules in our inputs time dependent sheet, which means we don't have to manually size and copy and paste that anymore. And all we have to do, since this is now based on hard codes, is hit our run all macro right here. And then within just 1 second, our macro runs all of these outputs as hard codes, which can be very handy for different decision makers. Great, guys, this was it for this lesson. And in our next lesson, we will tackle our next cases, which are cases 5 to 7, in which we consider a resource adequacy plus merchant arbitrage structure. All right, guys, I will see you in the next lesson. See you there.